now that you guys have. You did finish the homework, Tim?
This is actually the quiz. I didn't know if you wanted to take this.
Oh, yes, please. Yeah. So.
I submitted the quiz in your mailbox yesterday.
Oh, that's also okay. That's perfectly fine. Yeah.
Sorry, it's not stable. I didn't think about it.
Yeah, that's okay. There's only 3 people, so hopefully it should be okay.
Oh,
Yeah. Okay, let's see if I can focus. That's just once. Okay, what's up here? Ken and Rhoda, you guys on camera, sorry. You guys cannot see me. Sorry. Yeah, just once, I think. It's hard to capture all of you guys at one time. Okay, forget it. Okay, so did you get a syllabus again?
Yes, sir.
Yes, so you reached the website, that means.
Yes.
Okay, good. And where are you from?
I'm from Nepal, sir.
Nepal, good. Do you know anyone here who is from Nepal already?
Yes.
You've had grad students?
Yes.
Okay. Whom do you know?
Yeah, I know Yuvraj.
Good.
Person from India.
Good.
I'm in touch with them.
And?
I'm in touch with them.
Oh, you're in touch with them. Good, very good. Very good. Okay. And have you settled down here?
Yeah, already.
Okay. So you found a place?
Yes.
Okay. Did you get the email account here?
Yeah, I got that.
Okay, perfect. So you're in the system then, yeah. Okay, so this is math methods, as you know. So we had the first class last time. Half of the class we spent over the syllabus, going over the what will be the process logistics, and then mostly we want to do index notation. And is that something you've come across before?
No.
Summation notation? Okay, that's okay. There is a homework due on Tuesday. I know Ken has, it's on Tuesday?
Oh, Monday, 4:30.
Oh, sorry, Monday. Yeah, because I am still in the process that this class was supposed to be on Tuesday, and I've been thinking this is Thursday. No, this is Friday. So the homework is due on Monday. It depends on how much I can finish, but I think I'm planning to finish because there are these recordings. I can go a little faster, and then you guys can depend on the last year recordings and this year recordings that might be possible. So there is a homework. Have you started on the homework with it? Yes. So Abhiyan, start on the homework. If necessary, you can take extra time because it's the first, probably you'll be only having a few days, but catch up. Like, it doesn't mean that every homework you will get the extension, but yeah, feel free to take an extra bit of a few days. But there is a recording. Do you know that? Of the how do you reach the recordings? Do you know?
No.
Okay. Do you know the website for this course?
Yes.
Yes.
Yeah.
You know how do you reach there?
Yeah, I can.
You can. Okay. In that website, there is a link for recordings. Okay. So, or maybe I can show it here if you come on this side. I cannot put it on there, right? So if you come on this side, I can show it. So you know how to reach here. This is pix.com.
I can.
Okay, so that's the homepage, my homepage, right? If you click on 500A, that's the math methods, and you see lecture recordings.
Yes.
That's the lecture recordings you will get. So that's the first lecture as you go, 1, 2, 3, it will come up. I want to show one more thing, and Hruday, probably you should also be aware of this. If you go past courses,
Yes, sir.
right, there is 500A from 2020 fall. So last year's lecture course is available. There are recordings there also. There are problem sets there also. It's useful to be aware of that. Could you reach there? Yeah. Okay. So that's typically, I found that students find that useful. So feel free to do that. Okay. Yeah. And there will be a homework every 1 week or so, and there is a quiz which is due every class. Like for example, Ken has submitted this, and these questions are pretty much posted randomly in a class. It is not well posted, but you make the question clear. Just write it down, and small write up on the quiz is good enough. This is a detailed write up, even if it is half a page. So often it is just half a page. That's good enough. So I think this time there were more quizzes, 2 or 3 questions. Is that right? Yeah. So, so is that clear? So every time submit it here or in my mailbox. But this is convenient. If it's not inconvenient for you guys, give it in the class. That's easier. But homework, I think that is easier. The mailbox is easier because it is due at 4:30. Okay. Okay, so we were doing index notation. So let me. And this is mainly used for solving vector identities and in general playing around with tensor quantities. Vector tensor is a generalization of a vector. So we said that if you have a vector, so let's say there is a vector A, and this often you would say in terms of basis vectors. So you will say this is A1, and how do I? All right, let's say this is some basis vector E1 plus E2, E2 plus E3. And then you say that, okay, you get pretty much it's necessary that you have all the information for this, but then if you know the basis vectors, only in your back of your mind, you know that we are going to keep the basis vectors the same, then it's okay to say that, okay, we will always work with E1, E2, E3. And then we say further down that, okay, this is the same as AI. So it's just a compact notation. That's all it is, but it becomes very convenient and powerful when you reach tensors, especially when you're doing general relativity. You're doing tensors of 4th rank tensor where there are each of this, and you're in 4 dimension, 3 plus 1 dimension. So this is 4 times 4 times 4 times 4. And to play with that, it becomes very messy if you keep all the basis vectors. So this notation becomes very convenient. But it also comes at the price that you're fixing the basis, so you don't have a choice much to go from one basis to the other. But it can be done. It's just that you have to be more clever there. Okay, so that's your, if you want, this is the index. This is called the free index because this is really the component of a vector. How do we use this if you have 2 vectors? So we do dot product, right? So that's A dotted with B. And this we know is A1, B1 plus A2, B2 plus A3. This we say is the same as summation, or I is equal to 1 to 3 of AI times BI. It didn't have to be I, it could have been J, so that's good to realize that once you are in the summation notation, it doesn't really matter whether I call it I or J. So in that sense, here is a dummy indices. So now this is where the index notation really comes in. This is all fine, but you stop writing your summation notation altogether and say that whenever I is repeated, this is understood that there is a summation in there. And in this case, this is a dummy index because it's repeated. It's a dummy index. Here, this is not repeated, so it's a free index. So that plays an important role in realizing what a scalar is and what a vector is. So because it's a dummy notation, it's also equal to say that this is a j, bj. Even over this a little slowly last time, but I think that's the main idea. Okay, so how do we use this? Or okay, so that's your so a vector in general is AI. So this is components of a vector. That seems to suggest that, okay, that's I, which is only one variable. What if it was two variables? Then I can say, let me call B now, right? So B, I, and J. Now there are two indices. So I can take 3 values. J can take 3 values. So there are 3 times 3, there are nine components to that. So this has 3 components. This is 9 components. So these are components of this will be called a first rank tensor. So this is a second rank tensor. Now, the moment you say tensor, there's a whole field called tensor analysis, which is good. But broadly, it is pretty much a small generalization of this vector into that. It's not, at least the way we are doing it, it is not really deep. It is basically arranging, taking care of the components. That's all. We are not going very deep into the analysis part of it. So just to see what this is, this has 3 components, right? This is A1, A2, A3. That's 3 pieces, right? 3 components of a vector. What about Bij? It's good to organize it as a matrix. So this is B11, B12, B13, B21, B22, B23, B31, B32, B33. So that's the 9 components. A second rank tensor will always have 9 components, and they can be organized this way. And what I suggest is that in the beginning, this is a compact notation, right? This is a compact notation of this. This is a compact notation of this. Every time in the beginning, if you're not feeling, oh, I don't understand this, expand this out. Don't be lazy. Right? This is being lazy, but it has power associated with it. That's why we do it. But in the beginning, you want to get used to this. So expand this out in this form. It is tedious, but it will help you. Once or twice you do this, oh, this is what it means. And that's all there is to it. If you expand it, it's a matter of how you grasp that into your head and get used to that whole thing. Similarly, we can go higher tensors. Let me not call B. I'll just make it different. So this is C, I, J, K will be, this is the components of a third rank tensor, right? So this is third rank tensor. And now this is not easy to put this on a sheet of paper because the best is to make a cube, right? So you want to get out into the third dimension. So this will have how many components? 3 into 3 into 3, 27 components. And if you were working in 3 plus 1 dimension, 3 space and 1 time dimension, which is what relativity involves, then this becomes 4 times 4 times 4. So 16, 4 times, 4 times 4 times 64 components. And if it was a fourth rank tensor, then it is 256 components. And general relativity, which is what Einstein's equations are, they are written as a fourth rank tensor. The curvature of space-time, which you might have heard of, which is what general relativity deals with, that is a fourth rank tensor. And that fourth rank, so this whole thing was built to deal with that. In fact, this is this summation notation here. This is called Einstein summation notation. But nothing deep in there. I mean, this is just a the notation, basically just it's a notation that, okay, this is what it means. General relativity is deep, that's different. But here, this is just a process or a simple thing to deal with it. Okay, so that's your definitions now. So let's define some very useful tensors. So let's, the first, oh, I think I forgot to show this camera there. Okay, hopefully they will be able to refer to it afterwards. Okay, so yeah, whenever I change, sometimes you guys can remind me, but you guys don't see that. That's a challenge. So okay, I'll manage. I'll learn this. Okay, okay. This is called Kronecker delta. Delta symbol. So Kronecker delta symbol. And the way you would write this is delta Ig. There are how many dummy indices in this? Dummy indices. See, that is the word dummy and free, right? So there's a dummy index and there is a free index. Correct? Free index means it is not doubled. Dummy means that should be repeated. I is not repeated. J is not repeated. So these are not dummy indices. These are free indices. The way I think last time I was talking about is f of x. When you say this is a free variable, you call it. X is a free variable because a function depends on x. But if I now say integral dx f of x, a to b, whatever this is, it doesn't depend on x. So x is a dummy variable. I can call it an x or a y, it doesn't matter. Is that clear what I mean there? So in here, I and j matters. Whether I is equal to 1, I is equal to 2, it matters. So ij is free there. But we will, very soon I will talk about dummy indices. I'll give examples there, it will become more clear. Okay. So in this case, there are 2 free indices and no dummy indices. Correct? That's what. So this is a symbol, this is a definition. This is going to be equal to, so this is the first tensor we are introduced. This is a second rank tensor, right? This is not a vector. How many components does it have?
9.
9 components, right? 3 times 3. I can take 3 values, J can take 3 values, and I can arrange them as a matrix, right? And we are going to define this as 1, 0, 0, 0, 1, 0, 0, 0, 1. This is called the identity matrix, right? This is more simplistically written as this is equal to 1 if I is equal to j, and this is equal to 0 if I is not equal to j. Correct? Which can be arranged as a matrix. More appropriately, that is that. Is that clear? Maybe this, and this is usually an arrow. This is exactly equal to this, right? So I should have flipped it the other way. That usually you don't write a matrix equal to this, but it's okay. It's understood that. So it's clear. So now let's mix up, right? So now we have a tensor, and now I can manipulate this using index notation. So let's begin by saying, so I have an expression a I delta I j. What is that equal to? Okay. Now again I ask, there are how many dummy indices?
2. No.
2 or 1, I think you mean there are I is the only dummy index, but it comes twice, so that's what you meant by 2. Right? So I is a dummy index and j is a free index because j is not repeated. Okay, it's a dummy index in the sense I don't really need the i's, So how come I don't need the I? Okay, so what is this equal to now? Okay, so let's see what this is equal to. So it's at the beginning, it seems like A multiplying a matrix. So let's see what this is equal to. So there is an I dummy index. So immediately I say, oh, this means I is equal to 1 to 3. Right? So this is A1 delta 1j plus, this is included in 2 steps. So this is AI delta I. Right? This is what the index notation means. Now I expand this. This means that this is A1 delta 1j plus A2 delta 2j plus A3 delta 3j. Right? That's what it means. But what is A1 times delta 1j? If delta 1j, when does it survive? Like there is 1 or 0, right?
When
So
j is equal to 1.
when j is equal to 1, j can take 3 values. J is equal to 1, j is equal to 2, j is equal to 3. But when j is equal to 2 and 3, it doesn't contribute. Correct? So it is only when j is equal to 1, it contributes. Correct? So let me point that out. So let's say j is equal to 1. So this is a vector, or maybe I should ask before that. This whole quantity, how many components does it have? This whole piece here,
9,
how many components does it have? 12. So how do you get that?
3 into
9.
9
So this is 9 components.
multiplied then
3.
the 9 again.
So 27 components. Try again.
Not like that. Can it do like that? 3 times 9 or it will be 9 again?
Think. This has, I agree that this has 9 components.
Yes.
That's the second right answer. But this whole quantity, this boxed quantity, how many?
After multiplication we'll get the same 9.
So 3.
3. Yeah, and why is that 3? That's
That
correct.
was 0.
Because of the free index.
Because of the free index. Dummy indices doesn't matter. That's summed up. So it is only the free index that decides. So this quantity as a whole, I is not important. This quantity, whatever this is some vector j. Dummy is like after the integration, all the dummy variables are gone. This is the only thing that survives. So this is actually a vector. It looks like 3 components, but it's not. 2 of them are dotted, right? They are basically contracted or these are dummy basically, like summed up. So this is actually a vector that 3 components to that. And the 3 components are when j is equal to 1, j equal to 2, j equal to 3. Is that clear? Right? So let's investigate those 3 components. Right? So let's say C1, right? So when j is equal to 1, I can get C1, right? So this is C1 there. And if it is C1, so I have set j is equal to 1. So I've set j is equal to 1 now. So let's see what this is equal to. So this is A1 delta 1 plus A2 delta 2 plus A3 delta 3 Is that clear? So I basically substituted j is equal to 1 and what is delta 1
1.
1, good. Delta 2
0.
0, delta 3 0. So the 2 doesn't contribute. This is simply A1. Similarly, if you do C2, what do you get? Can you evaluate C2 quickly?
A2.
A2.
A2, good, because it will be A1 delta 1 2 plus A2 delta 2 2 plus A3 delta to 3. These two go to 0, that's A2. And similarly, C3 will be equal to A3. So what we learn here is that AI delta ij is actually equal to whenever this is simply aj itself. Right? This thing should be thought of as, if you want to think of it as a matrix, if you have a column vector multiplying a matrix, right? And is this giving any insight? This is a row vector multiplying a matrix. Is that clear? And if this was one identity matrix, what will you get? If a row vector multiplies an identity matrix, you get the vector again. Correct? So this will give you back the vector. This is nothing but that statement. This is an identity matrix multiplying a vector gives you a vector again, right? And this is that summation, like matrix has the summation, right? This goes and multiplies this, this goes and multiplies this. This is that multiplication process that we are writing, that's all, right? Nothing elaborate in that. Okay, so this you want to take home. This is a trick that now, even though once you should verify this, so this is how it will be. Once you have to do this explicitly, but then you learn that, oh, whenever I see a delta ij, whichever is getting contracted with, it disappears and this comes bj. Okay, that's the property of delta ij always. Another way to look at it is that this contributes only when I is equal to j. Otherwise, it doesn't contribute. So only when I is equal to j it contributes. So this is aj. So that's another simple way of arguing it out. But elaborately, that's what it is. Okay. Okay. So one more. Let's see. So let's write AI delta ij times bj is to, before we begin, how many free indices?
So both are repeated. Yeah.
Both are repeated.
Both are repeated, so there is no free index.
Yeah.
There are two dummy indices, I and j. So is this is a tensor of what rank? Is this a vector? Is this a tensor? And if it's not, remember, so there is a
Vector into vector.
yeah, vector into vector. But this is contracted, remember, right? This is dotted in a sense, but it's double dotted in a way.
Vector dot vector.
So how many components does it have? Maybe that's it's basically the free index that decides it. How many free indices?
None.
How many free indices I have, not components.
Free indices two. Or
There's zero for you.
Zero.
Zero free index, because both are repeated, right?
yeah.
So there are two indices here, I and j, right? Both are repeated. So how many free indices? Zero, basically.
Zero.
So there is no free index. If there is no free index, that means it is a scalar, right? It's a tensor of rank 0, right? No free index. Okay, so this is a scalar. That means this will, after you do everything, you will get just one number, not three numbers. This had three numbers. You will just get one number. Okay, so let's see what this is. But we already know how to do this, right? This piece here is nothing but here, right?
Mhm.
You know how to do that. So we basically know that whenever this structure comes in, I disappears and j the subscript of A gets replaced with J. So this is nothing but a J Bj. But that is assuming this went with this. I could have also done it with this. If I had done it here, I could have replaced J also, right? Bj delta Ij. So this is also equal to Ai Bi. Is that clear? So if I were to use this as my notation, I can put it the other side also. So either way I can go, but they're the same, remember. Is a dummy, doesn't matter whether it is I or J. And what is this equal to? This is in vector algebra. What is that equal to?
Dot product and
Dot product of A and B, right? So this is, I think we did that earlier there. Yeah, so this is A dot with B. Which we said earlier that this is going to be a scalar, there's only one number. That's what this is, right? So A dot would be B in terms of indices is equal to that. Okay, any questions on this? Yes.
Just to be clear about the arrow above the variable. So we don't do that for our shorthand AIs.
No, AI is the components itself. This we won't write an arrow.
Right. Okay.
So this is more like saying this here. So this is when you expand this. So this is simply this, right?
Right. Okay.
So at this stage, you wouldn't write the arrows, right? There are the indices. So it's not really the vector that's in there. So yeah. Arrows are not there, correct? Yeah. Okay. Okay, so that's dot product, but and in vectors we also have cross products, right? So let's try to build another quantity for dealing with cross products, and this will be called Levi-Civita symbol. Is it Civita CE or CI? CE. So we constructed a second rank tensor, but basically an identity, right? That's the simplest object you could build, but very useful object, very powerful object, because identity matrix is a very powerful object in matrix algebra. Same thing now, we are going to build an antisymmetric object if you want. So that is a word we'll talk about that later. But now this symbol will be called epsilon. This is the Greek symbol epsilon, and it is a third rank tensor. It is I, J, and K. So clearly, this is if you were try to organize it as a matrix, this will be a cube matrix, like not really a planar matrix. This will be a cube structure, right? So not really a matrix. It's an array of third rank array. Now I have to define what this means. We will say this is equal to 0. The easiest one is that this is equal to 0. No, that's not. Let me begin with 1. So this is equal to 1 if how do you say this? Yeah, if I, J, K is cyclic. What does cyclic mean? If these numbers, if these indices show up as 1, 2, 3, or 2, 3, 1, or 3, 2, 1, so cyclic means so this is 1, 2, 3, right? So if the order of this indices is any one of this, so that means it could be 1, 2, 3, it could be 2, 3, 1, and it could be 3, 1, 2. Right? Any of these three this is equal to 1. So 3 components, it's equal to 1. So this is called a cyclic. This is equal to -1 if ijk is anticyclic. Is that the correct word? Anticyclic. Anticyclic. Okay, which means you go in the opposite direction. So this is 1, 2, 3. This time you go this way. Which means the components could be 1, 3, 2, 3, 2, 1, 2, 1, 3. In 3 dimensions, it is easy to think of this as going in a cycle, but when you go into 4 dimensions, you shouldn't take this as a cyclic at all. This has to do with permutations. So if you start with 1, 2, and 3, and how many permutations you need to go to 2 and 2, 3, 1? First, I have to flip 2 and 1, and then I have to flip 1 and 3. So 2 permutations means for every permutation, you get 1 negative sign. If you do 2, then you get, if you get 2, then it becomes plus. Because if you just switch once, so it's 2, 1, 3, you get here, that's -1. Right? Again, you switch 3 and 1, you reach here, so that's +1. So it has to deal with swapping indices rather than, but in 3 dimensions, it is easy to remember it as a cycle. And for some time, or here, for some time, you will be in 3 dimensions. But the moment you reach relativity, then it's 4 dimensions, and that's important. So don't make that mistake. This is equal to 0 otherwise. There are how many components for this tensor?
27.
27, right? So it seems like there are 3 of them which is +1 out of 27, 3 of them that are -1 out of 27. The remaining, which are 21 of them, are 0. The 21 components of this tensor is 0. Pretty much like the identity matrix. It's basically a nice handy object. Okay. So it's good to see this as a what do you say? As a, or let me just fix to that. I mean, I elaborate on how it actually this looks like, or the 27 components in the other videos. So go and look into it. I think this should be clear enough. But like have a picture of it in your mind. Okay, so how do we use this? Before that, maybe antisymmetry, right? This is an antisymmetric object in the sense that epsilon ijk is equal to, notice that I said that if you swap any of the 2 by construction, it swaps sign. So this is equal to minus of epsilon jik. Okay, so if you swap the 2 indices, then it becomes minus. For that matter, it doesn't matter which one you swap. So now if I swap it again, so let's say I and k, this is equal to plus epsilon j ki. Is that clear what I'm doing? Here I swapped once, I swap it again, it becomes double, so it is -1 raised to 2. So 2 swapping leads me to there. So j goes to I, then I and, so here I swapped I and j, here from here to here I swapped I and k. Is that clear? So this is antisymmetric. In all the indices, like I can take any one of them and swap them, and I will always get a minus sign. Okay, so here I did it with 1 and 2, here I did it with 1 and 3. I can also do it for 1 and 3. J and k I can swap. So in all indices. So that's called a completely antisymmetric tensor. When it is antisymmetric in all indices, then you say it's complete antisymmetry. Sometimes there is a tensor that is only antisymmetric in the 1 and 2. but it's not antisymmetric in 2 and 3. So then it's antisymmetric, but it's not a completely antisymmetric. Okay. Just in this context, we should ask, what about delta ij? What happens if I replace I and j in this?
You replace
Or swap I and j? If I swap I and j, what happens?
nothing.
Nothing happens, right? It is the same. So this is equal to delta ji. This means it is symmetric. And there are only two indices to swap. There is only one possibility there, symmetric tensor. Every tensor need not be symmetric or antisymmetric. Sometimes it does nothing, right? It does more than something. It is probably doesn't have any pattern at all that when you swap ij. In matrices, this will be a symmetric matrix, right? And you have antisymmetric matrix in 2 indices, but now this is in 3 indices, okay? Okay, good. So now let's see how does this help us. So let's go and think about a cross product. Let's think of cross product. So let's have A cross B. And let's say this is equal to C. Right? C equal to A cross B. Right? And what is the best way of, so what is this equal to in terms of A1, in terms of its components? What's the first component here? So then, A. So you will do the determinant, right? So there is a small notation and in there. So you would say this is B. Now A2 times B3 minus of
B2A3.
B2A3. And so let's say I don't write the component, right? So this is comma. So that's the first component, correct? The second component will be A1 times B3, but I write A. So
A3B1.
yeah, A3B1, right? So this is A3B1 minus B3. Let me write this as
A1.
yeah. So A1B3. I want to write it in a specific way. So this is A3B2. Yeah. So this is the next one is A1B2 minus A2 A2B1. So clear? But there is a pattern in this. The moment you see this, the first component is got, so this is the first component, right? 1. Think of 1, 2, and 3, right? The cyclic nature. The first component is gone by 2, 3, and then swap it, 3, 2. Right? The second component is go this way, 3, 1, and then swap it. The third component is go cyclic, always. Right? So if you're on the third component, go to 1, 2, and then stop it, right? So there is anti-symmetry in here inbuilt. So that seems to suggest, so what we have is C1 is equal to A2, A3 minus A3, B2, and C2 is equal to A3, B1 minus A1, B3, and C3 is equal to A1, B2 minus A2, B1. That's good. That's an observation. But can we capture this using our Lewis-Avita symbol? And let's propose. So the proposition is that Ci actually. So this is a component of the vector product. In terms of Lewis-Avita symbol is I, J, K, and then Aj, Bk. Okay. Now that's an equation. Let's start with the right-hand side. There are how many free indices on the right-hand side?
One.
Only one free index because I is the only free index. J is repeated, K is repeated. Right? So two dummy indices and one free index. Notice that whenever you write an equation, the free indices has to balance. If there is one free index on the left-hand side, there has to be one free index on the right-hand side. It's like if this is a vector, that has to be a vector. You cannot write a vector is equal to a scalar, right? That's never an equation. Right? If this side is a second rank tensor, that side has to be scalar. So the free indices has to balance all the time. Okay, so if this is the case, we should check, right? Is this really true or not? So let's check that whether C1 is indeed this is or not. So let's write I is equal to 1. So it's C1, right? Let's try what is C1. So that's equal to epsilon 1 jk times aj bk. If I is equal to 1, we notice that all this, so these are the only terms which give you non-zero values for Lewis-Avita. Whenever, in particular, whenever something repeats, there is never a repetition here, right? Whenever an index repeats, that's 0 for sure, right? So if I have chosen I to be 1, j cannot be 1. J has to be 2 or 3, and k has to be 2 or 3. So there are only two possibilities here, right? So if j is equal to 2, k has to be equal to 3 because it cannot repeat again. There are only two possibilities. That means to say that this can be 1, 2, 3, or this can be 1, 3, 2. That's the two pieces. Remember, there's a summation, right? There is a summation on j, so 3. There are 9 terms in here in the sum. But although those 9 terms, 7 of them are 0. Is that clear what I'm saying? Okay, there is a sum here which involves epsilon 1. 7 of them are 0 because they have repeated index. So only 2 of them survive, and they are A2, B3, and this one is A3, B2. Think about that. If that is not very clear, explicitly do that sum. This is a sum. Write that explicitly and verify that for yourself. But this is equal to 1. And that's equal to minus 1. That's equal to A2, B3 minus A3, B2. It's correct. Right? Similarly, you can verify C2 is indeed is equal to epsilon 2 jk aj bk. And again, you can say that, oh, when you sum it up, once you have set I is equal to 2, j and k can be only 1 or 3. So again, you do that and you will verify. So this is, let's say this is quiz homework, right? Or not, this is a quiz. You complete complete this, verify that C2 is actually true, and verify that C3 is so verify this. Right? Verify. And if you get stuck in this, if there is any confusion, look into last year's video. There I go in detail and verify this explicit. Okay, nice. So now we have a dot product and a scalar product. So now we should be able to process, put these things together, right? So now let's see what we can do. So we have A dotted with B cross C. Right, that's a vector identity. Is that a scalar or a vector?
It's a scalar.
It's a scalar, right? A vector dotted with
Vector.
right? Yeah, good. So that's now right. So this is a dot product to begin with. So this is AI times, let me say B cross C. So notice the notation. This is a mixing of notation. There is a vector which has 3 components. Is that clear what I mean? Like I should actually write this to be D, let's say, then this is AIDI. Right? Is that okay? This is no confusion. But this itself, I know what it is. This is equal to AI. And this is epsilon ijk bj ck. Is that clear what I did? How many free indices in this?
None.
None. So it's 0, which just makes sense because left hand side is a scalar.
Scalar. Right hand side.
So right hand side also has to be a scalar. There should be no free indices. So 3 repeated index. Good. All right. So this is equal to, but now I can play some games here. So this is epsilon ijk, and these things are each, so at one point, these things are numbers, right? So I can move things around. So AI can move to the right or to the left because these are components. Right? This is not really, like A cross B is not B cross C. Right? That is a negative sign. But here I can replace B and C because these are components. Right? So that's not very obvious. So verify that, check on that, that even though A cross B is equal to minus B cross A, when it comes to components, it doesn't matter. Right? These are just numbers, right? The components are numbers. You can actually put that wherever you want. So this is AI, BJ, and CK. Right. That's just one step extra I wrote. But now let's see what I can do. What I'm going to do now is just playing a trick here. I move K 2 times. First movement, I get a minus sign. Second movement, I get another sign, so it remains the same. So this is Kij times AI Bj. And that's CK. Is that clear? And I used parentheses for convenience for the next step that I'm planning to do. So the only thing I've done is I moved K or swapped K with I and J. Now this is a cross product again, correct? But now this is a cross product in A and B. So this is equal to A cross B. And this is the kth component of that. And that is C of K. Is it clear what I did? Which means that this is dotted now. This is A cross B dotted with C. So I proved a vector identity. which is sort of obvious, but still we used. And it seems like, oh, this is a long process now. But if you were to work it out with these components, you will see that that's a lot more work. And this is, at this point, it seems like there are 1, 2, 3, about 5 steps. But that's because we were doing it in detail. And very quickly, you will get very used to this, and you can do this in 2 steps. Okay. So these are the kind of problems you will have to work with. I'll tell you, prove that this is equal to this. Then you can use this notation to do that. You can explicitly do that using components. Each component you can verify, but that's much more work. Okay. Let's also do one more identity, the standard identity, that's A cross B cross C. Right? What is that? Is that well defined? What is missing in there?
Okay.
Nothing? Is it okay to write something like this? It's okay?
Yeah.
Seems okay? Actually not, because it's not very clear which operation comes first, right?
There has to be a parenthesis.
There has to be a parenthesis, correct, right? So A cross B cross C, because A cross B and then a C is not the same as A cross B cross C, right? So this is not the same as A cross B cross C. That's a parenthesis now, but okay. But that's a vector, correct?
Yeah.
So let's see what this is equal to, right? And there is a standard rule for this. Well, do you know what this is equal to actually as an identity? It comes often. It's remembered as back cap rule. So this is, so you would say this is back. So B times A dotted with C and minus of C times A dotted with B. The way to remember is that you have this quantities in parentheses, each one gets to be a vector. So this B and the dot the rest of the two, C dot the rest of the two. So suppose we have to verify this using our index notation, then you would go and do, right? So let's see if I can finish it here itself. So this is a vector. So I would say this is epsilon is equal to, left hand side is equal to, or let me go to the other board. I think we need more space. Okay. So A cross B cross C. This is a vector. So let me call the components as I, right? So that since it's a vector, there will be 3 indices. So that's only one free index. So let me call that free index to be I. You can start with anything, J or K or M or N, whatever you want. That's A cross B cross C. That's equal to epsilon I j k times aj, and then B cross C times K. That should be clear, right? That's just using the idea of cross product. Okay, with me? There? But this is also a cross product. So we go ahead and do this is epsilon I j k aj, and then this is epsilon k. Now I need 2 more letters. I've used I, J, and K, so I'll use 2 more. So let's say M and N. I got to be careful not to use the same letters, right? Because then it will be confusing. And that leads to, so that's two Levi-Civita symbols coming together. And before I proceed, I should also let me switch this K 2 times. So this is epsilon Kij. So I did two things. When I'm moving this here, then Kij, I can swap K 2 times, right? That's epsilon K Mn. Then there is Aj Bm Cn. And now we reach a stage where we are having two Levi-Civita symbols together, and we need some way to recognize what this is, right? So this shows up in your homework also. So in general, this is K is repeated, notice, right? Oh, by the way, this whole thing, let me, okay. So before we go there, let me go and do something else. I forgot that I should introduce that also. So we take a break there and we come back here. And let's do what is epsilon I j k epsilon L M N. How many dummy indices in that?
None.
None, right? There are no dummy indices.
6 free.
So there are 6 free indices. How many components to this? 27 into 27. So that's a big number,
Yeah.
but that's a 6th rank tensor. Okay, but many of them are zeros. Like 21 of them are zeros here, 21 of them are zeros here, and remaining are what is surviving, correct? And they have the symmetry property, anti-symmetry property. If I replace any two of them in this, they switch sign. Right? And there is something else that has a very similar property, and that's the determinant. Determinant of a matrix, if you replace two columns, they change sign. You replace two rows, they change sign. So determinant has exactly the same property. So one can verify, not really basically by checking it, one can verify that this is delta IL. This is a determinant of delta IL, delta IM, delta IN, and delta JL, JM, JN, and delta KL, KM, KM. So determinant. And again, that's, since this is a 6th rank tensor, it's not supposed to be straightforward, but most of them are zeros, right? If you were to calculate any one of them, there's a good chance that you will encounter a zero. Okay, so that's just an identity. Okay, I don't ask you to verify this in your homework, but starting from here, we can get some interesting results. So let's start with, let's set n equal to k. So let n be equal to k. That means I'm contracting this, right? So I'm contracting this, which means now I'll be summing it up. So I sum over k, that's what it means, right? Whenever the k index is repeated, it is summed over. So, and so this becomes epsilon ijk times epsilon, oh, actually, not let me say L and M because I want to connect it with that, right? So just because I have a purpose, so I set k is equal to L, right? Not N. I can do anything there, right? Set any of the two the same. If I set I is equal to J, what happens? I is equal to j, not swapping.
Zero.
0, because the moment that two are the same, it is 0. Very good, right? It's an antisymmetric object. If they're the same, they will be 0. So only possibility is that I contracted with that, right? So if I set k equal to L, this becomes epsilon k mn. And now I can move k 2 steps on this. So this is kij epsilon k mn. And that's the same as this quantity that I need to process this scalar product. So that's equal to pretty much do the same expansion here, except that wherever I see a L, I had to replace a K, correct? So a determinant is, first I start from here, and then I write this as a determinant there, correct? So I'm going to expand that. So this is delta I LSK, and that's delta Jm, delta Kn, minus of delta Km, delta Jn. Is that clear? So it's simply multiplied by that.
But
Yes.
can you please explain the parenthesis?
Oh, what I did is, how do you take the determinant? You start from here,
Mhm.
then you find this times this minus this times this. The next one I'll start from here, and this times this times this, and then this, the determinant of, so I'm just, to clarify that I wrote that parenthesis. So, okay, so this is, you would say this is minus delta In, that's delta JL times delta Km minus Kn. And minus of delta KL delta Jn. Yes, Christian?
Is the L a K?
L a K. Oh, L is a K. Good. Thank you. So this is a K. Shouldn't forget. This is K. Thank you. And then there is plus delta In and these two. So again, L is a K, JK, Km minus of delta KL, delta Km, okay, K. Good. Okay, we have only 7 minutes. I should make an announcement that homework, I had to postpone the homework to Tuesday. Oh, sorry, Thursday. No, Friday. Friday. That should help again also. So, because I think I remember there's a gradient also in there. And,
Gradient card.
yeah. So if I had finished this, then I could have done that, but I had forgotten about this. So I am supposed to introduce this also. So yeah, so you guys have more time. Okay, but let's do this. Let me start with something simple here. Okay, there is a delta KK here, right? What is delta KK? Delta KK?
It's one.
Think again. Index notation. Don't forget.
Yeah.
Index notation. Anything that is repeated,
It's summed over.
it's summed over. Yeah.
So it's 3.
So it is 3, right? Why it is 3? Because this is equal to sum over, right? Sum
Yeah.
over k equal to 1 to 3 delta kk. That means it is delta 1 1 plus delta 2 2 plus delta 3 3. That's 3. Okay. Yes, Christian.
Yeah, so we assume the 3 dimensions.
Yeah, that's we are assuming. All this is
Even
3-dimensional vector.
Okay.
If it is 4-dimensional vectors, then we need a Levi-Civita symbol of the 4th rank.
Understood.
Okay, so I think there was a homework. Did I ask you that? What is the cross product in
Yeah.
in
4 dimensions.
in 4 dimensions
And in 2 dimensions.
and in 2 dimensions? First of all, 2 dimensions. How do you do a cross product? Because it has to go out of the plane, right?
It's
Then
not
it becomes
possible.
tricky. Yeah. So unless the space is embedded in a 3rd dimension, if the 3rd dimension is available to you, Only then you can define. Otherwise, there is no
So, yeah.
there's no cross product there. In 4 dimensions, now you're many of the, if you're in one plane, then you can be in another. There are many other planes available. So there's a 4th rank tensor that's
But
that you can
the
construct.
cross product is also not defined in 4th dimension.
In principle, yes, it is not. You have to define many of them.
Yeah.
Like it is not unique. I think that's the way to set it. It's just because there is no one plane there, right?
Yeah.
So how do you define it? Yes, exactly. Good. So what do you define? Yeah, go ahead.
I was just going to add, it's interesting to note that you can do a cross product in 7 dimensions.
Oh, really?
Yes.
I think cross
Okay.
product is closed under 3 dimension, also under 7 dimension. 3 dimension.
I'm not aware of this. Okay, good to know. Okay, and any insight on that? How?
Okay, but I have a question.
Uh-huh.
If it is closed under, I mean, cross product is defined at 3 dimension and 7 dimension,
Yeah.
is it defined in 15 dimension? I mean, is there a pattern or something?
Why 15?
I mean, 3 plus 3 and you add 1, it's 7.
Oh, I see. I don't know. I did not even know that 7 dimension is closed. I do know that in 4 dimensions it is not, because you cannot construct it, right?
Yeah.
The simple idea of this thing.
Perpendicular.
Oh, 7 dimension. That was 7.
Yeah, it's like
I don't know. How about this? New quiz, right? So let's say, so this is what I said. There is something called, look up
Yeah, quaternion.
quaternions.
Yeah.
Right? Quaternions, I think I don't think I'm pronouncing it. Quaternions.
quaternions, yeah.
Quaternions and octonions.
Yeah.
Right? And the math department, there is Jurek Kochik, Jerzy Kochik. Okay. He's an expert on this. I'm just telling it so that you have someone here who does it. But find out what's the connection between cross product and quaternions, and how. So there, the point is that you cannot go beyond octonions. So there it is and it is not even, you're not working like cross product at all. So the question I'm raising is that, is there a connection between you saying that's in 7 dimension, the cross product is closed, and the idea that quaternions, there also the algebra is closed in quaternions and in the 8th dimension, which is the octonion. So is there a connection? Or why is cross product closed in 7 dimension? I will also check it out. I don't know the answer yet.
You lose a property, I believe. So with
You-
quaternions, you lose commutative.
Yes, that's correct.
And then the octonions, I think it's associative. I think you lose both.
You lose
commutative
both.
and
I
associative.
don't remember
I
it.
can't
Yeah.
remember.
Yeah. So check it out again. Remember that this is a quiz. You don't have, this is not a project. Okay? So don't spend all your time on it. But yeah, be curious, and on your own, if you enjoy it, read it. Otherwise, just submit 2-3 lines on this. But that's interesting. Yeah, I will try to come up with something with decent answer if I can, but I might not be either. Yeah, but good. Yeah, good question. That is there any pattern in that? Is that, does it happen again?
Yeah.
Is there anything written there? No, they just know what 7. So
I
probably
could-
7 is unique. 7 out of. Oh, yeah. Okay. Good. Okay, that's good information. So I was not aware of that. By the way, do you guys have class after this?
Oh, yeah, I do. I
So-
have 11. Or something.
Yeah.
Okay, so you also have.
Yeah.
Okay, so we have to stop now. This is bad. Okay, that's okay. So we will stop here and
Yeah,
then
but-
come back. No, I think this will take a
Oh,
little time. Yeah, I think I don't want to hurry on that. It's okay. Since I've anyway postponed the homework, I now have the whole of Monday's class, and we will work on that. And that will let Abhiyan catch up also. Okay, good. So was it okay, Abhiyan?
Yes, sir.
Right? You will catch up. Yeah. You only missed one class. We didn't
Yes,
do
sir.
much.
I'll cover from.
Yeah, we didn't do much there. So, but us, Ken and Hriday, yeah. Did you meet Hriday?
Yeah.
Yeah.
Can
Okay.
you earlier?
Okay. Good. Yeah. Okay. Good. Enjoy. And
Thank you, Professor.
Good. So that.